So I'd like to thank the organizers for the invitation to speak at the workshop. And I'd also like to thank Matthew for introducing several of the concepts that I'll need in the course of the talk. I can hopefully go a bit faster over those things. So the talk is about the augmented index problem. It's a two-party communication problem where the input is split between Alice on the left and Bob on the right. You can sort of imagine it as the following scenario. You have, you're trying to look up the phone number of a friend, and you pull up the address book on your phone, but some software glitch causes part of the phone book to disappear. You have some guess for what the phone number is, and you have, of course, everything, you have, let's say, the first half of the phone book, but there's no way to verify what the phone number is, except to call, let's say, the directory, the telephone directory. So question is, how much communication do you need? Meaning, if you call the telephone directory people, I forget what they're called in France, there's a number in the US and Canada, 411, that's what we call for these things. Question is, how much communication need there be between these two for the second party, let's call him Bob, to be able to verify whether his guess for the phone number is correct. So a simplified model for this scenario is where the phone directory is a sequence of n bits. The second party, Bob, is interested in the kth bit of the sequence, has the first k minus 1 bits, and a guess little b for the kth bit. And the question is whether his guess is correct, meaning the kth bit of the string x is indeed b. I can formulate this as the computation of a Boolean function, which is simply the XOR of these two bits, x sub k and b. If the XOR is 0, then the function value is 0, meaning the two bits are equal, and otherwise the function value is 1. It's a very simple problem, but turns out that it occurs in a host of settings, both in communication complexity and as a result of reductions to communication problems from other areas, like from data structures trying to prove the optimality of the size of the data structure versus the number of queries you need to make to it, or things like state tomography, or size of quantum finite automata, formula size, and so on. So it seems to be a very fundamental problem, and studying it for its own right is actually perhaps going to lead to some gains down the future. So how might we try to solve this problem? There are two simple protocols that immediately would spring to mind. One is where the first party, Alice, sends the entire n bits to Bob, and then he can simply do the verification on his own. The second one is where Bob sends his index k to Alice. Okay, the second one is, well, in terms of communication, more efficient because the index needs only log n bits of communication. There is an interpolation between these two extremes where, in the first case we had n bits of communication, in the second we had log n. Instead, you could do the following. Let's say Bob only sends the m leading k bits. So he has the index k. Of these log n bits in k, he sends the m leading bits. Now, you can think of the m leading bits as indexing some blocks of the n-bit string, meaning you break up the n-bit string into 2 to the m blocks, and the message that you receive tells you which block it is that k lies in. So Alice sends the corresponding block, which is of length n over 2 to the m, to Bob, and he can then figure out the value of the function. Now you can further ask, is this the best possible protocol, given that Bob is sending some small number of bits m to Alice? How much really does she need to send back to him, so that he's able to compute the function correctly with some reasonable probability of success? Turns out, if you think hard enough about it, it seems unlikely that you can improve over this, and in fact there are some related results that exactly pin this down. I'm going to talk about a similar result in the setting of quantum communication. So the result is the following. Let me just say it's a bit informal out here, but as we go along, I'll try to make things, one concept formal at a time. So let's say you have a quantum protocol that solves this augmented index problem. Let's say it has t rounds of communication, meaning there are t alternations of messages between Alice and Bob, at the end of which they determine the value of the function with probability at least 2/3. So they might make an error with probability 1/3. The claim is that in any such protocol, one of two things must happen. Either Alice reveals n by t squared bits of information about this string, or Bob reveals so much information, which is 1 over t squared, about his index. This other part, the prefix, is of course known to Alice already, so there's not much to be gained about that. As a consequence of this theorem, we are able to derive a lower bound for streaming algorithms for an important problem called Dyck 2. And the lower bound that we get is square root n over t cubed, where t is the number of passes over the input that the algorithm makes. OK, so as I try to make things more formal, let me start with this connection with streaming algorithms, which might be not very familiar to several people in the audience. So streaming algorithms are a model to deal with massive data sets, where the input is so long that your computer, which has memory which is much smaller than the length of the data in comparison, cannot really store the entire input in random access memory. And so it's forced to look at parts of the input. And perhaps a good way to infer properties of the input is to do a quick scan of the input left to right. So we think of the input as arriving, in the case of bit inputs, 1 bit at a time. And then your computer, which has limited memory, looks at your bit, the current bit, and it has some information stored in its memory. It does some computation using its memory, and then moves on to the next bit. The goal is to keep as small a memory as possible in comparison with the input length, and determine some property, interesting property of the input. So it turns out that the augmented index function arises from a study of a particular problem for streaming algorithms. And this was discovered with Frédéric Magnier and Claire Mathieu back in 2010. So if you think about this model a bit, and you're familiar with quantum, not quantum, but finite automata, you'll recognize that when the memory of this computer is of constant size, then the languages or the problems that are solved by it correspond precisely to regular languages. And so the question that we considered was whether you can use streaming algorithms to study languages beyond or more complex than regular languages. In particular, whether we could, with small memory, recognize the set of well-parenthesized expressions over two types of parentheses. And this language is called Dyck 2. So for example, you might have a sequence of parentheses like this, consisting of round or square brackets. And the first example here is, you can very quickly verify, well-formed. The second one is not, because you start with a round and a square, but the next parenthesis is a closing round one, which should have been a square instead. Okay, as these expressions grow bigger and bigger, verification is not quite as straightforward. And the question is, how much space do we need in this model to be able to do this quickly? So this problem is well studied both in mathematics, combinatorics, and in computation. And it turns out it's also very useful in practice because it captures this idea of checking syntax of large pieces of text. So in 2010, we discovered that we could test whether a given expression is well-formed or not with sublinear memory, in particular square root n memory for length n expressions. And we could do it really fast. We could do it with polylog n time per symbol with just one scan of the input left to right. And surprisingly, when we allowed one extra pass, so we considered a two-pass algorithm, we were able to reduce this space requirement exponentially to log squared n. The caveat was that the second pass had to be in the reverse direction. So you had to read the input first, going forward, and then the second time going in the reverse direction. Moreover, we showed that you could not replicate this kind of space usage with just one pass, meaning if you considered a streaming algorithm, regardless of how much time you allowed it to take per symbol, it would need square root n log n space. For actually, I should qualify square root n log n space, provided it was correct with probability something like 1 minus 1 over polynomial in n. Now, a natural question is, if you allowed yourself more passes of the input, could you then again recover this logarithmic space algorithm? And two sets of authors out here, including me with Rahul Jain, showed that regardless of how many passes you allowed the algorithm, as long as they were all in the same direction, you needed essentially square root n space. The savings you could get would only be in the number of passes you allowed. Now, in both these cases, where we showed lower bounds for the space usage, the lower bound came about through a result of the sort I stated before, meaning we showed trade-off between the amount of information each party has to send about their input to the other in order to derive this. So let me try to explain a little bit more formally what it means for a party to reveal information about their input. So this, the information that's revealed is quantified in terms of a notion called internal information cost. And I forget what Matthew called it in his talk, but it's the analog of CIC. what he called CIC, which corresponded to quantum protocols. Okay, so we imagine that the inputs to the two parties are distributed according to some joint distribution. X is the input for Alice, Y for Bob. And we look at the protocol that is supposed to compute your function. We consider the history of messages that are exchanged, and let's call the random variable corresponding to that as t. Now, t is random because there's randomness in the inputs, x and y, and also because the protocol itself is randomized. So we are looking at classical protocols for now, and shortly we'll come to quantum ones. The information revealed by Alice, which we call the cost for Alice, is measured by the mutual information of her input with the classical transcript. Now, this is conditioned upon the input for Bob. And the idea is that you would like to measure the additional information that you get about X through the transcript over what you got by the correlations between X and Y to begin with. And similarly, you can quantify the information revealed by Bob. And this is the information, mutual information of Y with the transcript given X, which is Alice's input. Now, these two quantities would, of course, depend on the probability of error that the protocol makes. And we won't dwell too much on this. For the rest of the talk, we'll assume that, at least for the results that are presented, the probability of error is fixed to 1/3 for Boolean functions. Now, something you might have noticed in the statement of the result, and I'll point it out again, that this measure here of cost, of course, depends on the distribution over inputs X and Y. We'll be looking at this cost with respect to what looks like a baffling distribution, one where the function is actually constant, and in particular 0 for augmented index. Okay? And the idea is to bound or find lower bounds for these two costs with respect to this input, but for protocols that actually are correct, meaning given an arbitrary input to the function, not necessarily a 0 input, it could be any mixture of 0 or 1 inputs, the protocol should compute correctly the value of the function. Okay, so a number of trade-offs were known for the function augmented index prior to this work, all in the classical setting, and there's one in the quantum setting I'll get to in a bit. Let me maybe just say, pick one of these and tell you what it looks like. So you consider, let's take the last one out here, which is the most general of them all. It says the following. So consider any protocol, any classical protocol for augmented index. It has any number of, it may have any finite number of rounds of communication. You allow some constant probability of error, let's say 1/3. And you look at how much information is revealed by one party, meaning the information cost of, let's say, Alice, given the information cost of Bob. It says either Bob has to send m bits of information about his index, or Alice reveals n by 2 to the m bits of information about her n-bit string. And this corresponds exactly to that trade-off that I had shown in a protocol a few slides ago. Now, all of these measures of information are with respect to first the internal information cost and the computed for the uniform distribution over 0 inputs. So the reason So okay, I should go back here. You know, so these results motivated Rahul Jain and me to look at similar information cost trade-offs for quantum protocols for augmented index. And the reason was that you know, this model of streaming algorithms is also very attractive in the quantum setting, in the sense that you know, quantum computers, at least the ones that are built initially, are likely to have very few qubits and very low coherence time. So the idea of quick processing with a quick scan of the inputs with small memory is precisely the kind of thing that we might be able to do with you know, with quantum computers of the near future. And moreover, the model allows you to do some non-trivial things, meaning go beyond regular languages in terms of computation. And in fact, there's good reason to study such algorithms in the quantum setting, in addition to sort of, you know, what was shown a long time ago about quantum finite automata. There are problems which are much more complicated, where it was shown that quantum streaming algorithms need much less memory, exponentially smaller amount of memory as compared to classical streaming algorithms. And so the question for us was, does this also happen for Dyck 2, which is a fundamental problem and is of practical interest? So, so turned out we were successful in showing an information cost trade-off for quantum protocols, and it looked like the following. So for the same distribution over zero, uniform distribution over zero inputs, correctness probability at 2/3, and T-round protocols, we showed that either Alice reveals n over t information about her n-bit input, or Bob reveals 1 over t information about his log n bit index. But there was a problem. The problem was that this did not give us the lower bound for streaming algorithms that we were hoping for. And there were other sort of conceptual issues with the definition of quantum information cost that we used. It was quite specialized to this function that we were studying. And then, you know, it was not clear whether it also captures the connection with communication complexity. We could also look at other notions, and we did think about that and noticed that for other notions, for example, this CIC, that the connection to streaming algorithms did work. But on the other hand, we could not show a result of that nature for this other notion of information cost. So we lacked either a good notion of information cost or the tools necessary to analyze them. So we solved all these problems in the work I'm about to describe. So I'd like to sort of address each of the sort of shortfalls of or shortcomings of this result one by one, starting with the notion of information cost. So let's look at quantum protocol in more detail. We've seen this in Matthew's talk earlier. This is a two-party communication protocol between Alice and Bob. You can imagine the setting of computation of a Boolean function where Alice is given an input. She stores it in some register A sub in. Bob gets another input stored in B sub in. Now these are distributed according to some probability distribution, but we think of creating a coherent superposition with a purification in register R, a reference system R. Okay, so when R is traced out, A in and B in correspond to the random variables X and Y, which are given to Alice and Bob. They also share an entangled state and you can think of this shared entangled state, which is in tensor product with the inputs, as containing the workspace which will be used in the protocol. And then they alternately perform some local operation and send some qubits across and continue doing that for some number of steps, here m steps, after which some part of the final quantum state is considered to be the output. So in particular, measurements are included in this. You can think of computing a Boolean function by simply having these registers A and B out to be single qubit registers that contain the output. And the question is, what is the probability that these bits equal the value of the function you want to compute? OK, so I've already described how this protocol looks in the case of a Boolean function computation. Maybe I'll just leave it here for a second for it to sink in. There's one point on this slide that I would like to highlight, which is that for our analysis, it'll be sort of important to assume that these protocols are in a certain form, meaning when we're looking at classical inputs x and y, we ask that these local operations, which are unitary operations u sub I, are read-only on these inputs, meaning they are controlled by these registers and may only write in the remaining, in other registers. So what is information cost for such a quantum protocol? It's quite similar to the notions we saw in the previous talk. It's, we look at the protocol message by message. Let's see Alice's messages, for example. Those messages, at least in this diagram, are all the odd-numbered messages. They are in registers C sub I. We quantify information in this register C sub I by looking at the conditional mutual information with the reference system given the recipient's Bob's register at that point, B sub I. Now, why should this correspond to any notion of information revealed? Well, in the case of this Boolean function computation, you might take R to be sort of a canonical purification, which is simply a coherent copy of x and y. And in that case, R here, especially for Alice's input, will have a classical random variable x, with respect to which we are measuring this mutual information. Okay, now the rest of it, the rest of the definition may not be as intuitive, but it turns out this is the right notion of information cost in several scenarios, and in particular in the one we are about to look at. Okay, so the main result, cast in terms of this notion of information cost, which was due to Dave Touchette back in 2014, is the following. Any quantum protocol for augmented index with error probability 1/3 on the uniform distribution over all the possible inputs has information cost at least n over t squared for Alice or 1 over t squared for Bob when you measure it with respect to 0 inputs, where t is the number of rounds in the quantum protocol. Okay, a few things about this result. I have maybe 10 minutes to try to give you some idea of how the proof works. The high-level intuition and the structure of the proof is basically that in our previous work with Rahul, meaning we had the right idea, but we didn't have the right tools or the right notion to work with. And the right tools are, of course, this notion of information cost, in addition with a few innovations out here, one of which is this superposition average encoding theorem, which is, well, we'll see this shortly. It's quite an intuitive lemma about quantum protocols, which follows from this breakthrough result by Omar Fawzi and Renato Renner from 2015 on it's now the name is eluding me. Let's see, on recoverability. Let's see. So we use this this tool with some non-standard use of the reference system, and it turns out to be sort of helpful in making the argument go through. And we also use inspiration and also some technical lemmas, the relationships between different notions of information that were developed in this work by Dave and Matthew. Okay, so let me jump directly into the intuition, and then I'll tell you what, you know, in what I present, or the simplified version I present, what is actually not accurate, and how it's fixed, and with what tool. So let's look at this scenario, a very simple quantum protocol, where you have only two messages, and we give inputs to Alice and Bob, which are distributed like this. We pick X uniformly at random. It's a random n-bit string. We pick a random index k from 1 through n, and then we set this guess little b for Bob to be equal to the kth bit of X. Now this is an input, or this is a distribution over inputs, where the function evaluates to 0 all the time. Okay, it is with respect to this input that we were measuring information cost trade-off. Now, why would you expect there to be a trade-off at all? It's because of this. So imagine that both information costs from Alice and from Bob were small. So they're not sending much, they're not revealing much about their inputs. Then what we'll do is we'll construct inputs where the function evaluates to 1, but on which the final state, the joint output of the two parties, is actually close to what we have on 0 inputs. Okay, that'll mean that the output, the single bit output that you're producing, is not correct, because they'll be distributed nearly equally in the two cases. Okay, so how do we use the fact that there is low information sent? Let's look at the case of low information, or small amount of information being revealed from left to right, from Alice to Bob. So what we'll do is we'll look at two distinct inputs for Alice. And what I'm describing is going to be patently false. It's not really how it works, but it at least tells you what the idea is. So we'll think in terms of fixed inputs. Okay, so let's take this input X, and we'll think of Bob's index being some j, which is in the first half of the string. So the idea is that if the first message has very little information, little o information, so sublinear information about the string, then it's unlikely that it contains any information in the suffix beyond x from 1 to j minus 1. Okay, so if those bits in the suffix were uniformly random, then Bob will not be able to tell what those bits are. Okay, so a little more formally, if these are quantum bits, and results in a joint entangled state between the two parties, what happens is that Alice can implement a local unitary transformation on her part of the register so that the joint state in the two cases where you have string x versus another string, let's call it x prime, where I've flipped one of the bits in the suffix, the two states are close to each other. Okay, so you can conduct a similar argument, which is also, intuitively correct, but patently false. I mean, if you take it literally, it's not correct, but here goes. In this case, we are keeping Alice's input fixed to this string x, but we'll consider two different inputs for Bob, because we would like to see how much information is revealed in the second message, which is from him, about that input, about the two different inputs. What we can infer is that if MB has very little information about this index, then for a pair of indices J and L, one in the first half, the second in the second half, the messages, and in particular Alice's entire state, will look essentially the same, independent of the two inputs. And morally, well, similar to the previous case, it means that you can transform the joint state in the case of input J to be close to that for the input L by doing a local transformation on Bob's side. Okay, now how do we put these two things together to get a contradiction? Now, the actual argument is a bit more complicated than what I'll show here, and it's much simpler to assume that none of the two parties have any local workspace, meaning we are looking at a memoryless protocol. Okay, so there we basically have pure state messages, and we're able to conduct this argument with a simple hybrid argument or a triangle inequality. So let's go back to our original goal, which is to construct pairs of inputs, one where the output is 0 and one where the output is 1, but are such that the protocol states at the end are close to each other. So the 0 input, let's call x and index k, and let's call the final state C in this case. We'll consider a different n-bit string x prime, which is the same as x, except in the lth bit. Bob's input will remain the same. And by the argument that I made in the previous slides, if Alice's cost is low, we can argue that the final state C prime, in this case, where Alice's input is different, is actually close to what we had before. Now we consider another pair of inputs. Here we start with x and k. We keep Alice's input the same, it's x, but change Bob's input to L. L is in the second half, k is in the first half. So in the first case, our final state is the same as here. In the second case, it's C double prime, let's say. What we'd argued is that this switch from k to L, I'd called it J before, but it's the same. This switch from k to L does not result in too big a difference between these two states, meaning C double prime is quite close to C. Now, what we'd like to argue is that when we simultaneously switch Alice's input and Bob's input, from x to x prime and k to L, the final states still remain close to each other. And this is how we do that. So I have a sort of more detailed description of what the states look like, assuming there's no memory in the protocol. So Alice's, the output state in the first pair of inputs, where you have inputs x and k, is this. Alice applies u sub x, Bob applies v sub k. And similarly, for the inputs where we switch x to x prime, keep k the same, or keep x the same, switch the index, or switch both the index and the n-bit string. So those are 4 states that we have. We have argued that these two are close to each other. We have also argued that psi and psi double prime are close to each other. Let's just call their distances in the L2 norm to be delta. And we'll show that phi, where both inputs to Alice and Bob are different from that here, is also close to psi. Okay, and it runs through, it follows from this set of triangle inequalities. So this difference, the norm of the difference, is bounded by the sum of 2 norms, where we are comparing the distance to the intermediate state psi double prime, okay, where we've switched only Bob's input. Now look at the first term, psi and psi double prime. We'd already shown that these two are close to each other up to delta. Now phi, and the sort of relatively non-trivial part in this argument is bounding the second distance. Okay, so here Alice's input is L. Bob's input, Bob's index is L. Alice's input. So in both cases, both pairs of inputs. And Alice's is x prime in one, x in the other. Okay, so the L2 norm is unitarily invariant. So this distance is the same if we replace Bob's unitary transformation by identity. And in fact, replace it by some other one. Replace it by the one he would have applied. This is not particularly visible, but he would have applied if his input was k and not L. Okay? And if you do the switch, you end up with the states psi and psi prime, which we had shown or argued were close already. Okay, so you get a bound of twice delta on the distance between these two inputs, but these two inputs corresponded to 0 and 1 inputs of the function. And because the function was being computed correctly by the protocol, this gives us a contradiction. Okay, now this simple intuition and argument actually doesn't work as is. There are lots of details that lead to technical hitches. And maybe I've run out of time, so I won't go over all of them. Maybe I'll just point out one of them. And maybe not this one. Another one where we had to sort of go beyond earlier intuition and earlier tools, which is to do with this informal statement I made about a connection between low information cost and distance between the states at the recipient's end. It turns out that in the argument that I made, for technical reasons, we need to fix a prefix of x to some uniformly random string, and then ask for the remaining bits to be in superposition. Okay, in particular, something I didn't mention, the kind of sequence of triangle inequalities I showed you needs such a coherence in this suffix of x, okay, especially when you consider protocols with memory. So that actually creates a hitch in making this kind of argument, which we address with this what we call superposed average encoding theorem. Now, the statement of the theorem, at least informally, is quite easy to understand. What it's saying is that if you have a protocol in which one party is revealing very little information about her input, let's say delta input, and this is done incrementally over t rounds, measured with respect to this notion of quantum information cost, then what you can do is you, as in the recipient, can simply ignore all the messages and try to reconstruct the final reduced state on his part with very high accuracy. And what's the accuracy? Well, it's square root of t times delta. Okay, and this sort of a theorem you can derive using the Fuzzy-Renner inequality. And this is one of the places where you see that we get a dependence on the number of rounds, on the information cost. Okay, there are several other details. There's the connection to streaming algorithms, but I'll skip all of that and wrap up. Maybe some things I'd like to say is probably this dependence on the number of rounds is due to the tools that we are using. It's very likely that the bounds that we have are not optimal, but we don't have the right techniques to improve, to remove this dependence on the number of rounds. The streaming lower bounds that we get, we in fact show that the classical algorithms are almost optimal. There's probably a potential for some improvement in the number of rounds, but that's about it. And we hope that the tools that are developed in studying this problem, they will be useful in other situations as well. So let me wrap up with this. Thank you.